Hello and welcome to this video about the electric field. We are going to talk about electric field strength, electric field lines, conductors in electrostatic equilibrium, and what a Van de Graaff generator is. So let's start with an electric field. An electric field is just a region in space around a charged object in which a stationary charged object experiences an electric force because of its charge. And here we have an equation that defines the strength of the electric field. We represent strength of electric field with a capital E. And when we look at this situation where we have this charged object with a capital Q creating an electric field, and we have this small Q naught point charge located here, capital E is the strength of the electric field that's being produced by this object and experienced at this point by Q naught. And it is equal to the magnitude of the electric force acting on Q naught divided by the charge of Q naught itself. The SI units of the electric field strength are newtons per coulomb. And remember that the electric field is a vector quantity. The direction of the electric field strength at a point is going to be equal to the direction of electric force that would be exerted on a small positive charge. We call that the test charge. So Q naught is the test charge placed at that point. And here you can see that the electric field strength is there is a repulsive property here. So it's in this direction. Here, there is an attractive force. So the electric field strength is going to be going in this direction. And so you always think about the vector pointing, where is it in relation to this test charge, the Q naught? Is it going to be this way or this way? In this case, it's attractive, and in this case, it's repulsive. And the question, why do we assume a small test charge? Here, I tried to make it small and still be able to fit the plus sign in there. We always assume a very small test charge because if we use a large test charge, that can cause a redistribution of the charge on our large Q, our charged object, and that would change the electric field strength. What if we would like to know the electric field strength when there isn't a large object that's producing this field, but it's another point charge, kind of like our test charge. We have we have a point charge producing the electric field. In that case, we can use our Coulomb constant that we learned about before, and this would be the equation where the electric field strength is equal to the Coulomb constant times Q in this case will be the charge that is producing the field, not the test charge, but the one that's producing the field, and would be a point charge, divided by the distance squared between the charge and our test charge. There is our Coulomb constant in case you forgot that. Notice that the sign of Q is going to be important. If we have a positive sign for Q, for the charge that is producing the field is going to be directed outward radially from Q. If the sign is negative, that's going to indicate that the field is directed toward Q. And we'll talk a little bit more about that in the next frame. For an electric field due to more than one charge, you're simply going to apply the principle of superposition, like we have done before. And also notice that from our equation, an electric field is at a given point that only depends on the charge of Q, which is the object setting up the field, and the distance r squared from the distance between those two objects. So as a result, we can say that a field exists at any point near a charged body, even when there is no test charge at that point. And that's an important point to remember. Let's do an example together. In this example, we have charge 1 that is 7 microcoulombs at the origin and a charge of Q2, negative 5 microcoulombs on the x-axis, 0.300 meters from the origin. So we can look at it this way as shown. And we're supposed to find the electric field strength at point P up here. It's on the y-axis, 0.400 meters from the origin. So that has been drawn here. So this problem is a good example of how we can apply the principle of superposition to calculate the electric field due to both of these point charges. First, we're going to calculate the electric field produced by each individual charge at point P, and then we're going to add those two together as vectors. I'm not going to rewrite, just for the sake of space, all our knowns because they're kind of right here. Also notice we know that theta is 53.1 degrees. We're given that. But I'm going to look at the electric field strength for that Q1 is producing on point P. In order to do that, here's my equation. I'm going to take the Coulomb constant times the charge of Q1 divided by the distance between Q1 and P. I'll call that R1 squared. That will be 0.400 meters. Notice that when I plug these values in, I just changed the microcoulombs into coulombs. 1 meter is equal to 10 to the negative 6 microcoulombs. And my distance is in meters, so that is going to work well for my units. I get 3.93 times 10 to the 5th newtons per coulomb for the strength of the electric field that is being produced by charge 1. For the strength of the electric field produced by charge 2, I'm going to plug in the value of the charge that is being produced by charge 2. And the radius, in this case, the radius 2 squared is going to be this distance here between charge 2 and point P. And this is what I get for the electric field strength produced by charge 2. Next, let's think about the direction of our electric field vectors. And there's a little error here. These should be E for electric field strength, not F. It's also the direction of the force as well. But if we look at the field vector E1, it's going to be positive and pointing directly upward. Electric field vector 2 here is pointing from our point toward Q2, and so it would be negative. I need to consider the direction of the electric fields because I'm now going to find the x and y components of both of the electric field vectors. E1 is very easy. I can see that there is a 0x component, and all of the component of it is in the y direction, and it's positive y direction right here. So it's 3.93 times 10 to the 5th. We'd found that up here, newtons per coulomb. When I consider the electric field strength 2, I am going to redraw this line down here and then draw the x and y components for that vector. And I know theta, which is really nice and convenient. I know that the cosine of theta is going to be equal to the x component of E2 divided by the electric field strength of 2. So I'm going to rearrange this. I'm going to plug in the value of 53.1 for theta. For E2, I'm going to plug in the value of 1.80 times 10 to the 5th. That's what we found up here. And I'm going to solve for the x component of electric field strength 2. And I get this value, and it is going to be positive in the positive x direction. I'm going to do the same thing for sine of theta. Plug in the value of 53.1 degrees here. In this case, my electric field is going to have a negative value. So I'm going to plug in a negative 1.80 times 10 to the 5th. And my answer will be a negative value. That makes sense because the y component is pointing down in a negative direction. Now I need to add the components together in order to calculate the magnitude of the total electric field strength. So I'm going to add the two x components together and then the two y components, and I'll do that on the next frame. And you can see the x component's pretty easy because we have 0 in the x component for E1. And here is my now total in the x direction for the electric field strength in newtons per coulomb. And when I add the y direction together for each of the field strengths, I get 2.49 times 10 to the 5th newtons per coulomb. Notice that the y direction was negative for E2. I'm going to just draw these two vectors, the total for the x direction and the total for the y direction, and remind myself that what I'm finding now is this vector right here, the resultant vector. I can use the Pythagorean theorem to find this vector. Simply say this squared plus this squared equals this squared. And I can plug the values that we just found in for these. And don't forget to take the square root. Once you find this side of the equation, take the square root of both sides and solve for the total electric field strength. And then I can find the direction of that vector. I can, I'm going to call this theta prime just to distinguish it from our other theta in this problem. And tangent of that theta is going to equal EY total over E sub x total. And we get that theta prime as being equal to 66.6 degrees north of east, or in a positive direction above the positive x-axis, however you want to specify that. And last, does this answer make sense? And just a little reminder, the electric field strength 1 and electric field strength 2 were here from our previous page. If we look at our setup where we had the two charges and the point P, the electric field at point P is the result of a positive and a negative charge. So E total should be somewhere between E1 and E2. And it indeed is. Here's E1 and here's E2. Now let's take a look at electric field lines. Electric field lines are lines that represent both the magnitude and the direction of the electric field. Just by convention, these lines are drawn beginning at the positive charge and going toward the negative charge. You can see that here. Here would be going toward the negative. Here is a picture, a little diagram showing the electric field lines in the vicinity of two equal positive point charges. And here are our rules. We're going to look at a few rules for drawing electric field lines. As we said, they must begin on the positive charge or at infinity. And they must terminate on the negative charges or at infinity. So they are going from the positive to the negative. By convention, they are also drawn so that the electric field vector, E, remember our electric field vector, is tangent to the lines at each point. And the number of lines drawn is proportional to the magnitude of the charge. Also, where E is stronger, the field lines are very close together. So right here, where the field lines are closest together, the electric field strength is the strongest, and where the lines are furthest apart, the electric field strength is the lowest. And the number of lines drawn is proportional to the magnitude of the charge. Also, no two lines from the same field can cross each other. That's another rule. Here we have a representation of the electric field lines for 2 point charges of equal magnitude but opposite signs. And we just happen to call that electric dipole. That would be this configuration. Here is a picture showing grass seeds aligning with a similar field produced by a charged body as this diagram with a positive and a negative. In this case, only half the lines originating from the positive are terminating on the negative charge because the positive charge is twice the charge, twice as big. It's 2 times Q as the negative charge. So now let's take a look at electrostatic equilibrium in conductors. Conductors are in electrostatic equilibrium, meaning that there is no net motion of charge occurring within them. Remember, conductors are things like metals. These are the properties of conductors in electrostatic equilibrium. We're going to take a look at each one of them. The first is that the electric field inside of a conductor is zero everywhere. And we know that that has to be true because if that were not true, if there were an electric field inside a conductor, then the free charges, they would move and a flow of charge or a current would be created, and then the conductor would no longer be in electrostatic equilibrium. The second property of conductors in electrostatic equilibrium are that any excess charge that there might happen to be would reside entirely on the outer surface of the conductor. It is not inside, but it's on the outer surface. The third property of conductors in electrostatic equilibrium is that the electric field just outside a charged conductor is perpendicular to the conductor's surface. And this diagram here speaks to that. In this case, the electric field is not perpendicular to the surface of the charged object. This is the charged object, the conductor, the metal. And there is a component of this electric field that is going to be along the surface. And that's going to cause charges to move because of that component. However, in this case, you can see that E, the electric field strength, is perpendicular to the surface and charges are not moving. They are in equilibrium. And the last property we're going to talk about is that on an irregularly shaped conductor, the charge is going to accumulate where the radius of curvature of the surface is smallest. In other words, at sharp points on the object. And let's look at the next frame and see the picture to understand that better. So here is an irregularly shaped object. It has one end that is sharper. And excess charge tends to accumulate at that end. And that results in larger charge per unit area and a larger repulsive electric force between those charges at this end. And last, a Graaff generator is simply oftentimes used in physics just to generate electric charge. You can see in this picture what happens. This person is insulated from the ground and they are touching the dome of this Graaff generator here. And their hair is standing out on end. Why? Because the strands become charged and they then repel each other. That hair is trying to get away from each other. If you want some advanced ideas, how does a Graaff generator actually work? How does it generate that charge? Or how do microwave ovens work? Why would a microwave oven heat up a bowl of soup but not a dry plate? Look forward to seeing what you come up with, and we'll see you in class.